Welcome back to Quantum. Today, we're diving into the fascinating world of quantum computations, exploring how qubits, quantum gates, and operations like the controlled NOT CNOT gate and controlled U gate form the foundation of universal quantum computation. We'll also reveal how approximating unitary matrices and the universality of quantum operations shape the future of computing. In quantum computing, qubits, unlike classical bits, can exist in a superposition of 0 and 1, enabling quantum computers to perform multiple calculations simultaneously. Quantum gates control these qubits, with single-qubit gates handling the fine-tuning of individual qubits, and the CNOT gate creating connections and interactions between them. This ability to influence qubits and generate entanglement is essential for quantum computation. The controlled U gate extends this concept by applying a unitary transformation to the target qubit, enabling advanced quantum algorithms. Approximating these transformations requires breaking them down into simpler steps using two-level decomposition, ensuring even the most intricate quantum computations are manageable. At the heart of quantum computing lies the principle of universality. Any quantum operation can be constructed using just single-qubit gates and CNOT gates. Together, they form a universal toolkit, empowering algorithms like Shor's and Grover's to tackle problems classical computers cannot solve. First, we discuss the controlled U gate. We start by exploring one of the fundamental concepts in quantum computing, the controlled U gate. This versatile quantum operation builds on the well-known controlled NOT or CNOT gate and extends its functionality to any unitary transformation. Let's break it down. We begin with the controlled NOT gate, often referred to as the CNOT gate. It's a two-qubit operation consisting of a control qubit and a target qubit. The control qubit is represented by a line with a black dot, while the target qubit is shown with a symbol indicating the NOT operation, which is a direct sum sign or a boxed X, where X is the Pauli matrix sigma 1, which, as we have seen, represents the quantum NOT gate. Thus, the CNOT gate performs a NOT operation on the target qubit, but only if the control qubit is in state 1. Mathematically, this is described in equation 4.20, where the state of the target qubit is flipped conditionally based on the control qubit. Now let's generalize this idea. Instead of applying a simple NOT operation, imagine applying any arbitrary unitary matrix U to the target qubit. This is the essence of the controlled U gate. Similar to the CNOT gate, the controlled U gate has one control qubit and one target qubit. The controlled U gate applies the operation U to the target qubit only if the control qubit is in state 1. This operation is described mathematically in equation 4.21. The concept of the controlled U gate isn't limited to a single target qubit. We can extend it to multiple target qubits. For example, figure 14 shows a controlled U gate acting on multiple target qubits. The operation U is applied across all target qubits simultaneously, but only if the control qubit is in state 1. For example, the CNOT gate can act on multiple target qubits. In this case, all target qubits are flipped when the control qubit is 1, as shown in figure 15. What happens when we introduce more than one control qubit? This is where the Cn of U gate comes into play. It involves n control qubits and k target qubits. The operation U is applied to the target qubits only if all n control qubits are all equal 1. Equation 4.22 formalizes this process, and figure 16 illustrates an example with 4 control qubits and 3 target qubits. In most cases, the operation is conditioned on the control qubit being in state 1. But what if we want the operation to occur when the control qubit is 0? This is also possible. The control qubit in this scenario is represented by an open circle instead of a black dot. Interestingly, this configuration is equivalent to the original control condition when the qubit is 1, but with 2 X gates added before and after the control qubit. Figure 17 demonstrates how this works for the CNOT gate. Approximating unitary matrices. Next, we're taking a deep dive into a fascinating result in quantum computing, how single-qubit unitary matrices can be approximated using just 2 simple quantum gates, the Hadamard gate and the T gate. This concept is not just theoretical, it's a cornerstone of quantum gate universality. Let's unpack the details step by step. Before we begin, it's essential to understand the power of universality in quantum computing. We'll show in the next section that CNOT gates combined with single-qubit gates form a universal set of quantum gates for any number of qubits. But here's the exciting part. Even within single-qubit operations, you don't need an infinite variety of gates to perform any operation. Instead, the Hadamard and T gates are sufficient to approximate any single-qubit unitary matrix. The Hadamard gate and the T gate are deeply connected to rotations of the block sphere. The T gate corresponds to a rotation around the z-axis, while the composition of the T and Hadamard gates forms a rotation around the x-axis. By combining these two rotations, we achieve a new rotation r hat n of theta, where hat n is a specific axis in the block sphere, and theta is the rotation angle. This direction and angle are given in the second line of equation 4.23. Here's where things get interesting. The angle theta is an irrational multiple of 2 pi. Why does this matter? Because it ensures that repeated applications of the rotation r hat n of theta densely fill the entire group of rotations. In simpler terms, by repeating this operation enough times, we can approximate any desired rotation to arbitrary accuracy. This is mathematically formalized in equations 4.24 and 4.25, where the error is the distance between the desired rotation we want to reach and its approximation. The goal is to make this error smaller than any specified threshold, epsilon. But what if our desired rotation involves a different axis? That's where the Hadamard gate comes into play again. As shown in equation 4.26, the Hadamard gate transforms a rotation along one axis to a rotation along another, which is its mirror with respect to the plane xz. This allows us to create sequences of rotations along this new axis, ensuring we can approximate any single-qubit unitary operation. We recall now that an arbitrary rotation can be expressed in the standard zy decomposition, which can be subsequently transformed into an nm decomposition, where hat n and hat m are two non-parallel real unit vectors in 3 dimensions. Finally, we combine all these results. Equation 4.28, together with equation 4.23, demonstrates how any arbitrary unitary matrix U can be decomposed into a sequence of rotations using H and T gates. And here's the kicker. The Solovay-Kitaev theorem guarantees that this approximation can be achieved efficiently, with the number of required gates scaling logarithmically with the desired accuracy, as shown in equation 4.30. Why is this important? Because it tells us that quantum computations don't require an infinite variety of gates. A small, well-chosen set of gates is enough to approximate any operation. This principle underpins the design of universal quantum computers. Universal quantum computation. Next, we'll explore the concept of universal quantum computation, the foundation of quantum algorithms and circuits. By the end of this video, you'll understand how a small set of quantum gates can approximate any quantum operation and how these gates combine to create powerful quantum computations. In quantum computing, a set of gates is considered universal if any unitary operation, no matter how complex, can be approximated to arbitrary accuracy using circuits built from these gates. The universal set of quantum gates includes the Hadamard H gate, the pi over 8 T gate, the phase S gate, and the controlled NOT CNOT gate. With just these 4 gates, we can perform any quantum computation. Let's dive deeper into how this works. Universal quantum computation relies on 2 fundamental results: 2-level unitary decomposition. Any unitary operation acting on a d-dimensional Hilbert space can be broken down into a series of simpler 2-level unitary matrices. These matrices act non-trivially on a 2-dimensional subspace while leaving the rest unchanged. Universality of single-qubit and CNOT gates. Single-qubit gates, when combined with CNOT gates, can implement any 2-level unitary matrix. Together, they form the foundation of quantum universality. Let's explore these results in detail. First, regarding the 2-level unitary decomposition. As a concrete example, we consider a unitary matrix U acting on a 3-dimensional Hilbert space. We can decompose it into a product of 2-level unitary matrices, each affecting only 2 qubits, i.e. unitary matrices acting in a 2-dimensional subspace. For example, starting with the matrix U given in equation 4.31, we construct smaller matrices step by step, The first matrix U1 eliminates the matrix element B in the original matrix as shown in equation 4.33. The second matrix U2 further simplifies the structure by removing the matrix element C1 as shown in equation 4.34. The third matrix U3 is then given trivially as shown in equation 4.35. This approach generalizes to d-dimensional spaces where up to d times d minus 1 over 2 two-level matrices may be needed. See equation 4.36. While computationally intense, this decomposition is fundamental to implementing arbitrary unitary operations in quantum circuits. Next, regarding the universality of single-qubit and CNOT gates. We want to see how single-qubit gates and CNOT gates come together to implement any two-level unitary operation. Again, as a concrete example, let us take the unitary matrix acting on 3 qubits shown in equation 4.37. This matrix primarily affects only the two quantum states, say 000 and 111, which are also denoted by the Dirac-Ketz S and T respectively. The corresponding two-level unitary matrix, denoted U tilde, operates then in this reduced subspace, and it is given by equation 4.38. Here's how the unitary matrix U is implemented. Shuffling states with CNOT gates. Using a series of CNOT gates, we transition the initial states to intermediate states, as shown in the gray code sequence in the example. Applying the core unitary operation, a controlled U tilde gate applies the desired operation to the target qubit, conditioned on the control qubits. Unshuffling states. Finally, another series of CNOT gates restores the states to their original configuration. This method can be generalized to any n-qubit system, enabling the implementation of any two-level unitary operation. The gray code is what corresponds to shuffling and unshuffling and allows us to connect the initial and final states S and T such that consecutive states differ in exactly 1 qubit, as shown in the table in equation 4.39. The quantum circuit which implements the unitary matrix U is shown in figure 18. This quantum circuit has 3 main parts: state transformation. First, we transition from G1 equals 000 to G3 equals 011 using 2 CNOT gates. The first flips C if A and B are both 0, and the second flips B if A is 0 and C is 1. Unitary operation U tilde. Next, U tilde acts on A when B and C are both 1, mixing G3 and G4, which is equal 111. Unshuffling. Finally, 2 more CNOT gates reverse the initial transformations, taking G3 equals 011 back to G1 equals 000. This process demonstrates how CNOT gates and a single controlled operation can implement a two-level unitary matrix in a 3-qubit system. To implement a two-level unitary matrix U on n qubits using single-qubit and CNOT gates, the process follows the same steps as in the above example. Start with U. U acts on 2 states S and T with the corresponding 2 times 2 matrix U tilde. Gray code connection. Identify gray states Gi, connecting S to T, where consecutive states differ in 1 qubit. Shuffling with CNOT gates. Use CNOT gates to transform S to the state just before T. Core operation. Apply the controlled U tilde gate on the differing qubit. Unshuffling. Reverse the shuffle with CNOT gates to return to S. This approach uses n-squared gates, showcasing how basic operations build complex quantum circuits. Conclusion. Here's the big picture. Using just single-qubit gates and CNOT gates, any unitary operation can be broken down into smaller, more manageable components. This fundamental principle lies at the heart of quantum computation. While the number of gates required may grow with the size of the system, this method demonstrates that quantum computers can achieve any computation permitted by the laws of quantum mechanics. Universal quantum computation is a cornerstone of the field. By decomposing complex operations into two-level unitaries and leveraging the versatility of single-qubit and CNOT gates, this approach enables quantum algorithms to solve problems beyond the reach of classical computers. Thanks for tuning in to Quantum. Don't forget to like, share, and subscribe for more insights into the incredible potential of quantum computing. See you next time.